Okay, let's go ahead and get started on fuel as soon as the camera powers up. All right. TLO, action, describe the components, operational characteristics, functions, limitations, and emergency procedures of the CH-47D fuel system. Condition, in a classroom, given an operator's manual, and a student handout. Standard, correctly answer in writing without reference 7 of 10 questions pertaining to the components, operational characteristics, limitations, functions, and malfunctions of the CH-47D systems in accordance with TM 1-1520, 240-10, and a student handout. Safety requirements, none. Risk assessment level, low. And environmental considerations, none. And of course, for the evaluation, each student will be evaluated on this block of instructions during the 3rd written examination. This will be a criterion type examination requiring a go on each scorable unit, and you will have 90 minutes for the exam. Any questions? Learning step activity 1, describe the general characteristics of the fuel system. As we look at the fuel system, just like all our classes, we're going to break it down first for our pre-flight value. When we look at the fuel system, what you're going to find out is we have on each side 2 auxiliary tanks on each side and a main tank. The right main tank is going to feed the right engine and the heater. The left main tank is going to feed the number 1 engine and the APU. Now, one of the things I like to do with this class is basically, as we're looking at it, we've got 2 processes we're going to be talking about. We've got a feed process and we have a refueling process. If you think about the fuel system in those 2 processes, learning this system makes sense. It's really easy to understand. But keep in mind, the transference of fuel from the aux tanks to the main tanks is nothing more than what type of operation? The transference of fuel from the aux tanks to the main tanks is nothing more than what type of operation? What did we just discuss? There's 2 operations, feed and refueling. It's a refueling process, gentlemen. By thinking about it as a refueling process, you're going to understand the pieces and parts and everything's going to make sense. Okay? The airframe system furnishes fuel to 2 engines. The heater, we already talked about that, 2 separate connections for the cross feed and the transference of fuel during refueling operation from the right side of the aircraft to the left side of the aircraft. So what we have is we have this line right here, which is going to be used to transfer fuel through the D1 receptacle to both the right side tanks and over to the left side tanks. That's all that line's allowing for, which means this line is only going to be used during what operation? Refueling operation. Okay? Now, the crossover line, which is this line right here, is going to be used during what process? Okay, but during the feed operation, feeding fuel, keeping in mind that the crossover line is going to be used under pressurized fuel. Only now, depending on which way we got the fuel going, that pressurized fuel is either going to be coming from the left tank to both engines or from the right tank to both engines. Does that make sense? Why is that important to understand? Those engine-driven fuel pumps, these engine-driven fuel pumps are not sucking fuel out of the opposite tank. So therefore, it's got to be pressurized fuel through that crossover line. Any questions about that? And we're going to nip one little bit of confusion in the bud, hopefully, here this morning in just a little bit. So as we look at our tanks, we got our forward aux tank, our aft aux tank, and then we have our main tank. And we're going to have the same thing on the other side. Keeping in mind, during weight and balance, when Larry taught weight and balance, basically what we did was we took the two forward tanks, then we took the aft tanks and the main tanks for coming up with our CG limits. Why? Because the tanks themselves, capacities for the aux tanks, are the same. So we can do that. All right, types of fuel, JP4, 5, 8, low lead, 100, and Jet A. We can use all those fuels, and the nice thing about it is we have no adjustments that need to be made to our engines. We can put that fuel in that tank and fly all day long. But keep in mind, if we use low lead, what else do we have to remember? What does my operator's manual say about low lead?
6 hours.
6 hours. 6 hours. Now, keeping in mind, why? Even though it's low lead, it still has lead. And what will happen if we allow it to accumulate is that lead will form deposits in our combustor chamber, and then resulting in hot spots, which is why we're limited to 6 hours. I've used low lead twice, but we didn't have to worry about it because we used it as a bag of gas. The next fuel we took on was the right fuel, so therefore we didn't have to even worry about it. But we did write it up just in case for the 6 hours. Any questions about that? Capacities themselves, the tank capacities. And this is fixing to change again, so we're going to put it out as it is right now. Okay, but keep in mind, this is going to change again. Okay. Now, why does it become a big deal? Because we know that there's actually a difference in fuel capacities between the left main tank and the right main tank. But you'll notice that right now they've got it equal. That's what we have it as right now in our Dash 10, but reality is it's going to change again. But everybody makes a big deal about that 4-gallon difference. It's really only a training tool. Because reality is, as long as we pressure refuel the tank or the system, that 4-gallon difference between the left main tank and the right main tank is really irrelevant. Meaning what? What causes the 4-gallon difference between the left main tank and the right main tank? And this is a trivia question, but they like to ask it, so we're going to make sure you know the answer. The tanks are interchangeable between the left side and the right side. Where the open port is for over the wing and refueling it, using the old nozzle and refueling it, because it's interchangeable, what happens is on the left side, it's slightly forward. On the right side, it's slightly aft. And with the angle of the aircraft, that's when that capacity difference becomes a big deal. But unless you over the wing refuel it, it really is irrelevant, because when you use the pressure refueling, they stop at the same spot, which is why they thought about changing the book. But you know how sometimes we get stuck on these certain questions that we want people to know and people to understand? You know why? 4 gallons of gas is 4 gallons of gas, you know, or fuel. Total capacity, 1,028, 1,033, depending on where you read. And that's the other factor that comes into a big play. Any questions about that? And we talked about authorized fuels. The only one that I added in there is JP5. We don't really use JP5. JP5 is classified as a special fuel, and it's just not available really. Now, why did we go from JP4 to JP8? Does anybody know?
Higher flash point.
Higher flash point. It's a safer fuel, which is why we went to it. But that's why when we talked about engines, we talked about that liquid-to-liquid cooler and what it brings to the table. With JP8 being borderline diesel, we had to preheat that fuel so that those those igniters can ignite the fuel relatively easily. Otherwise, we'd have to preheat it some way, because although we call it JP8, you have to understand is borderline diesel, which means it's got a very, very high flash point.
Jet A, is that the same thing as low lead?
Jet A is actually equivalent to JP4.
Because back in the question it says JP4, JP5, JP8, and Jet A, and it doesn't talk about low lead.
Well, this is an emergency fuel, not a regular fuel. That's why. Okay, the only time we plan on this or use this is in emergency situations. Meaning what? Meaning that's the only thing that's available and we need gas. If we know an airport or a area only has low lead, we're not going to plan on flying into there. Not unless we absolutely have to, which would be, we had an emergency that caused us to deviate to use it. Other than that, we don't plan on using it, and that's why it's not on there. Good question, though. Fuel probes. We have 3 fuel probes in each main tank. We have 1 fuel probe in each one of the aux tanks for a grand total of 10 probes. But now, how many, when we talk about the fuel selector, how many indications on the main tanks do we have? We only have 1. It sounds like a trick question, right? So basically what happens is the average of all 3 of those probes is what's sent up to the cockpit. That's what you're receiving up there. And just for, because some people have those IPs that like these questions, it goes from the aft probe to the middle probe to the forward probe and then up to the cockpit. So the forward probe is actually what sends the signal up to the cockpit, if you ever get asked that question. Not to be confused with low quantity. Low quantity is on the center probe of the main tank. That's the only place we got the fuel quantity. Any questions about that? Now, the only other thing is the aux tanks feed the main tanks, which feed the engines and their associated system. The right main tank feeds the heater, the left main tank feeds the APU. The aux fuel is only going to be transferred to the main tank. We cannot directly feed from the aux tanks to anything. Any questions about that? And we'll talk more about that here in just a second. Pumps in the aux tanks. You have pumps and they look like that. Not to be confused, the pumps themselves are the same. The pumps themselves are the same. They are electrically operated boost pumps. That's what they are. What changes is the housing in which they are mounted in. And we'll talk about the purpose here in just a second. Okay? And then each one of the main tanks has 2 pumps. Either one of them will maintain the pressure required for the system, which is why that first check of the day, that when we do the fuel pumps cross-feed check, that's very important, because that one of those pumps could have failed on the previous mission, and we would never know it if we didn't check it. Because either one of them will provide the required pressure to maintaining the fuel pressure the system requires. Now, the main pumps, are they required for flight? Are the main pumps required for flight? Okay, I got one nodding yes.
Below 6,000 feet.
What?
Below 6,000.
At below 6,000 feet, they are required. Excuse me. Above 6,000 feet, they are required. Below 6,000 feet, they are not required. The engine-driven fuel pumps will suck fuel out of those main tanks just fine. Now, are the aux pumps required for flight? Yes. Anybody else?
As long as you have fuel in the main tanks. No.
Okay? It's kind of a trick question, gentlemen. If we need that fuel to get us to destination, then yeah, we need the pump. Okay? If we can get to destination without all the aux fuel, then no, you don't. Why do we need the aux pumps, but we don't need the main pumps?
Get the fuel in the main pumps.
What?
To get the fuel in the main tanks.
To get the fuel into the main tanks. That is the only way of transferring fuel from the aux tanks to the main tanks. So if those pumps are inoperative, there is no other way of transferring that fuel into the main tanks. Everybody understand that? Any questions? And again, with the main tanks, keeping in mind that the right main tank is also going to feed the heater, and the left main tank is going to feed the APU. Fuel control panel. The fuel control panel, any fuel-related questions, the fuel control panel will actually give you all the answers that you need. If you haven't put 2 plus 2 together yet, that is also your fuel schematic. That is also your fuel schematic. So the aux tanks transfer into the main tanks, and the main tanks feed the engines. And you can see that. Another question they'd like to ask you is how many pumps do we have? All you have to do is count the switches. 1, 2, 3, 4, 5, 6, 7, 8. See, I can count. 8. What do you think the trick question is? Normally they ask you on the fly, and out of gut instincts, what's the number one answer that usually comes out? 6. Based on the fact that what?
6 tanks.
6 tanks. Okay? But each one of the main tanks actually has 2 pumps apiece. And then we have our pressure lights associated with our aux tanks, but keep in mind, how many aux tanks are those lights associated with? 2. We have 1 pressure light, 1 aux pressure light, but it's going to be indicating from both systems. Just keep that in mind. And we'll talk more about those lights in just a second.
It's overpressure or under pressure?
Under pressure.
So it's empty.
Or empty or a loss of pressure, yes sir. Okay, you're actually, we were going to talk about that in a little bit, but those lights are going to come on for 2 reasons. 1, because the aux tanks are empty, or 2, because the aux pumps have failed, or a aux pump has failed. Those lights will come on for both reasons. How do I distinguish between the 2?
Shut them off both, check them one by one.
You can do that, or if I have those lights and there's still fuel in the aux tanks, then it has to be a fuel pump problem. So if the light's on with fuel remaining in the aux tanks, then you got a pump problem. If the lights are on and there's no fuel remaining in the aux tanks, then it's did what it's supposed to. Master caution / advisory panel, keeping in mind that we have the 2 indications. We have the low level lights, and then we have the loss of pressure lights or fuel pressure lights. But keep in mind that when you get these lights are only associated with which tanks? The mains. And that's going to be on both of them, low level and low pressure. They're only going to be associated with the main tanks. They have nothing to do with the aux tanks. The aux tank indication is going to be on the overhead panel. And we're going to eliminate a little bit of confusion too here in just a little bit too. Any questions about that? Other instruments that we have up in the cockpit, of course, is our fuel flow indicator. Did we already talk about our fuel flow indicating system? We went into great details on how it works. But it is still part of the fuel system, so therefore we have to point it out. But we're not going to teach you how it works, but it is part of the fuel indicating system. You got your fuel quantity indicator, which actually has 2 different readings. It has an analog and a digital. Digital will be and always is total fuel. Analog will always be the individual tanks. which means based on this selector. We can select an individual tank, or we can leave it in total, in which case what happens to the analog needle? It buries itself. It'll go all the way down to 0, and it'll stay buried until we select a tank. Is there any requirement to select a tank? Nope, there isn't. Some IPs will tell you one way, some IPs will tell you another way. Bottom line is, once you become pilot in command, the only opinion that matters is what? Yours. That's why everybody aspires to be a pilot in command. Okay? Flight engineer. There you go. Now, out in the right forward inner tank area, you have your refuel station, operated by your crew members primarily. Allows us to refuel all 6 tanks and the internal tanks if we have IRFs 2. If the aircraft is not modified for IRFs 2, then we cannot single point refuel IRFs 2. Excuse me, the IRFs. With IRFs 1, you had to overwing it, or you had to pressure refuel it from the door, but you had to be very, very careful. With IRFs 2, you can refuel it as part of that same D1 receptacle in the right inner tank area. We can refuel the external tanks in approximately 4 minutes. Reality is, you're going to find out it's a little bit more than that. Why? Because that 4 minutes is based on 55 psi at 300 gallons per minute. Army trucks aren't capable of it. But where you have to be careful is the Air Force, the Navy, the Marines, and any one of our civilian airports that we may fly into can. But normally, when we fly into one of those places, we ask them to lower it. We don't normally push the limits. That way, there's no chance of busting lines or overpressurizing anything. So we normally don't push those limits. It just means that 4 minutes is going to take a little bit longer. Any questions about that? And we'll talk about the capabilities of that maintenance panel. Crossover line. Again, crossover line is going to be used to allow us to send pressure fuel from one tank to both engines. I'll say that again. It will allow us to send pressure fuel from one tank to both engines. That's what it does. Now, we have 2 crossover gate valves, and we'll talk about those in a moment. And that allows, again, both engines to be simultaneously fed. Now, where does the misconception come in? The misconception comes in that everybody thinks we're transferring fuel from one side of the aircraft to the other side of the aircraft. Where does that misconception usually come from? What adds to that confusion?
It says cross feed.
It says cross feed. What else? How many pressure lights go out with the cross feed open? 2, right? Kind of giving you the impression, if we're not sending fuel from one side of the aircraft to the other side, we're at least sending pressure to the other side, right? Now, what you're going to find out is it's based on where that pressure switch is located, which is why both fuel pressure lights go out. But we are not transferring fuel from one side of the aircraft to the other side, and we are not transferring pressure from one side to the other side. In actuality, you're going to find out we don't even pressurize our tanks. All we're doing is sucking that fuel out, and we're pressurizing it in the line up to the engine. That's what's happening at the pumps, contrary to popular belief. People are under the impression that we are pressurizing the tanks. We are not pressurizing the tanks. We are pressurizing the fuel in the lines up to the engines. Any questions about that? Okay. Now, the engine fuel shutoff valves. Electrically operated via what? Engine fuel shutoff valves, electrically operated via what?
Fire tool handle.
Fire pull handle. Everybody thinks that's a trick question, but it's not. Okay? The other thing about it is where does this come in for pre-flight value? In your checklist, it tells you that you're looking for one to be open and one to be closed. And I'll be honest with you. I used to set you up for failure all the time. And I used to be able to get away with it. How did I get away with it? Because in your mind, as long as one's open and one's closed, you're good to go. That's the misconception. And so I always sabotaged you by doing both of them. If I opened one that was supposed to be closed, then the one that was supposed to be open, I'd close. So you'd be looking for it, and you see one open, one closed. Good to go. Which showed me, and shows the IP, that you have a lack of knowledge of which one's which. Is that important to understand? Sure it is. Sure it is. You have to understand why one's open and why one's closed. It's easy to go through a checklist and say, yep, look for one to be open, one engine, the engine shutoff valve to be open, one, the crossfeed to be closed, and it specifically says it. So in your mind, you turn that into one's open, one's closed. So you go out there and you look. As long as one's open, then the other one should be closed. Or one's open, then the other one's closed. And so that's how I sabotaged you. I never did just one. And then, and hey, listen, why am I teaching you this? Because guess who else does this? Your IPs here do it. So you have to be aware of it. And oh, by the way, some of those high-speed flight engineers help these IPs train you. And some of them were brought up in the same school as I was. Okay? Now, why do you look for this one to be open? Why do you look for the engine shutoff valves to be open? Because the fire pull handles are in. There's no more tricks to that. Okay? So why am I looking for the crossfeed to be closed?
Switch is off.
The switch is off. It's that simple. Now, what I would do from time to time is I would just move one. I would just move the engine fuel shutoff valve. For the purpose of what? For the purpose I would want you to catch something's wrong. And then normally, you'll say, hey, these are both closed. We have a problem. So what am I trying to get out of you now? Well, which one's wrong? Which one's wrong?
Depends where the fire handle stands.
Exactly. So what was I initially looking for? It's so easy to say, well, what would you do about it? Oh, I tell the flight engineer. What are you going to tell the flight engineer? Oh, one of the valves is wrong? That's pretty silly. You should know which one, and you should know why. Now, reality is you pre-flight the cockpit before you pre-flight the aft cargo area. So therefore, you should have already taken note that fire pull handles were in. But if you went and confirmed it, I have no problems with that. Engine fuel shutoff valve is closed. It should be open. Fire pull handles in. Chief, we have a problem. Yes, sir. Yes, ma'am. You're right. That's what I was looking for. That's what the IPs are looking for, is an understanding of that system. Any questions about that?
Actually, I do. So you put the handle in that position and it's open. Say it's on the fire pull handle side, the fire pull handle's in, and you moved it to the closed position.
Yep.
Why can't I just move it to the open position? If I know the
Because you need to verify, is there something wrong?
Okay.
Or is it doing what it's told to be doing? Okay?
If you did it and you said, sir, I just did that to mess with you, then you would just go to it and then...
And actually, you know what I would do? When I used to train, I used to leave it that way. Why would I leave it that way?
Power on it should fix it.
As soon as you power up the aircraft, it's going to fix it. And that teaches you two things. So sometimes I would just leave it. And then that way you get the realization that as soon as we apply the power, as soon as you turn the battery switch on, because it works off the essential DC bus, that valve's going to close. or excuse me, it's going to go back to the open position. Why? Because the electrical has priority over the manual. Good question. Anything else? Defuel valve located on the right side of the aircraft. It's a good tool to be able to verify which side of the aircraft you're on. But reality is, most people don't use the defuel nozzles. They might have used it once, twice, maybe 3 times in their entire career around these things. It's easier to have the truck come out and suck fuel. When would we use the defuel nozzle? Sometimes when we want to fill up a gas can for doing what?
Burning pool.
Burning poop, okay. That's true. Heaters for tents. Fuel for vehicles. Why? Because sometimes vehicles are limited on where they can go, how far they can go. Sometimes it's easier to get an aircraft to a place to take on additional fuel, so sometimes we'd steal fuel from the aircraft. Keep in note.
We do a FARP, we take it up that?
What?
FARP?
No, no, FARP's a whole different setup. We would never use our aircraft tanks.
No, but if you got earths installed inside,
It doesn't use that system, no sir. It's a whole different set of fuels, it's a whole different set of setup altogether. But good question. Anything else? Reality is, if we're going to defuel the aircraft entirely, we're just going to have the truck come and suck it out. We're going to have to anyway, because the defuel will only allow it to go so far down. Any questions about that? And it has to be operated with the pressure operated, the electrically operated boost pumps. So it's a pain in the butt. Engine-driven fuel pump will suck fuel out of its associated main tank for as long as we're below 6,000 feet. We already talked about that. Is there any questions about that? And keeping in mind, each one of the engines will suck fuel from its associated tank. That was the old IRFS 1. This is a cool picture. I'm glad they put this in there. That's what we used to fly with. A makeshift pump board. And these are just the 600-gallon pods that used to go in the back of 5 tons and deuce and a halfs, 2.5-ton trucks. They just modified them, put them into here. That's all they did. Now, they had a fuel capacity of 580 gallons based on the fact that once we put it in the aircraft, because of where the nozzle fuel point was, it would only allow us to fill it up to 580 gallons. We could carry 4 IRFS 1 tanks. Now, the problem with this system is it was a non-crash-worthy system. For those that do not know it, we actually had to get a airworthiness release to be able to fly with it, which means we had to fly with restrictions. Those restrictions actually included no passengers. But we did it anyway, because that's the only way we could get the mission done in some cases. So even though the airworthiness release said that we're not to fly passengers, we did. And why? Because it was just a safety hazard, that's why. Now, IRFS 2 is a crash-worthy system, and it brings a lot to the table. What does it bring to the table? An entirely safer system in all the way around. IRFS 1, if I had $1 for every fuel accident we had, I'd probably almost be a rich man. Just in refueling those tanks, we'd spill fuel all over the place. Okay? A lack of attention, just for a split second, those tanks would be overfueled. And I'll tell you right now, guilty as charged. We were going on a TDY trip to Greece, of all places. Beautiful place. We stopped at Brindisi, Italy, to top off our tanks before we made the jump over the water to go into Greece. My crew chief said, slow down. I was at the door, told the guy to slow down. He slowed down. Crew chief said, stop. I looked at the Italian fuel pumper. I went like that. He looked at me and went like that. And the next thing I know, fuel was spraying up to the top of the roof. Okay? And it's quick. With these, with the IRFs 2, it refuels just like the aircraft does. It'll automatically shut off. It operates off of a bladder system with a Kevlar internal tank. In other words, what? It's not only crash-worthy, it's ballistic protected. And it operates just like the aircraft tanks do. Instead of carrying 3 600-gallon pods, these are 800-gallon pods apiece, and we can only carry 3 of them. And you'll notice there's a lot more information on IRFs 2 in your Dash 10 because they are a crash-worthy system. Any questions about anything we covered so far?
First one obsolete.
Pretty much, but some of the units still have them.
Really?
Yes, sir. Probably more likely in the National Guard and Reserves. I think most of the active duty units have transferred over, but it's like anything else. It's due to funding and basically whether or not the unit wanted to upgrade to them or not. If they don't have a major mission for either fat cowling, refueling other aircrafts, or extended range, then they may not opt to upgrade and they may not opt to buy them. So in some cases, the states may have not upgraded, so in which case they would have still had the 600-gallon pods. But which ones are which, I don't know. Learning step activity 2. Describe the operational characteristics and components of the fuel system, fuel tank. Fuel tank structures. As we look at it, you have your backing board. All that does is protect those bladder systems from chafing. That's all that backing board does. Okay, why? Because on the backing there, we're going to have our little rivets that are going to pop up, pieces of sheet metal. So there's just possibilities of things for it to chafe against, tear on. So therefore, that's what that backing board does. We have our tanks, our inner tanks, which is nothing more than a bladder system. And then we have our shells. That's what the system's going to consist of, and it's going to look like this. There's your backing board, and again, all it does is protect and prevent chafing. And it reduces the risk of anything cutting or slicing open those bladders. Now, inside the tank itself, we have those vibration isolators. They're just like the ones that are in the floor between station 200 and 400, 44 left, 44 right. And all they do is reduce the amount of vibration that's being transferred. And when you say reducing the amount of vibration that's being transferred, keep in mind that fuel in there can cause vibration just as well as the aircraft causing vibration. And if it prevents it going from one way, it's going to prevent it from going the other way. Okay, so all it does, those vibration absorbers prevent the transference of vibration. That's all it does. Any questions about that? And we're not going to make that any harder. Okay? We said that the system is crash-worthy. Part of the crash-worthy system is the actual attaching bolts. They are made to shear. Now, the problem is we are not 100% sure how much force it's going to take to actually shear them. Okay, we know that they're shear bolts. We know that the system itself is meant to shear those bolts and allow the fuel bladders and the fuel tanks to actually separate from the fuselage. And we're going to talk more about that. But those bolts allow that to happen. The other thing that makes this system crash-worthy is inside we have a bladder system. Why a bladder system? Everybody complicates the crap out of this stuff, but why a bladder system? What is it? It's nothing more than a big bag. That's all it is. So that when we have a hard landing or we crash, this bag is going to do several things. One, it's going to absorb the shock. Two, If those tanks bend or crack, this bladder is made to just fold up on itself or indent to absorb the deformities of the aircraft on its crash scenario or crash sequence. Any questions about that? That's the benefit of the bladder. Now we're going to go more into the bladder here, because we're going to actually tell you that this bladder system will withstand up to a 50 cal round. Okay? And what you have is a rubber inside, rubber outside, and then you have a series of burlap and raw rubber deposits. Burlap, raw rubber deposits, burlap, raw rubber deposits, burlap, raw rubber deposits. For the process of what? As that round penetrates through here, what's going to happen is that the burlap is quite simply going to do what?
Expand.
It doesn't expand.
Gonna react with fuel.
Okay, the burlap is only going to either separate or it may shred. Now, why is that important to understand? Because what's going to happen is with the raw rubber deposits, that chemical reaction has to have something to adhere to re-solidify itself. Otherwise, it could re-solidify itself, but the pressure will push it right back out and it won't do any good. So by having the burlap in there, it has something to adhere to and re-solidify it. To the tune of, they've had rounds go through these tanks and they didn't even know it until they did what? Huh?
Did their inspection every year, they going in.
Actually, they didn't even find it because the round was so small and where it came out, the exit hole, was covered up, so they never saw it. So how else would it have manifested itself?
Through your
Fuel
fuel
pump
sample.
failure.
Through the fuel sample. It turns that fuel sample to a bluish, grayish, greenish tint, depending on who you talk to. I personally haven't seen it. Okay? But that's how that bladder system works. Any questions about that? Okay, now, if I've got my shear bolts that are made to allow my tank to shear away and roll away, what are my next concerns in the system? What else do I have to allow to happen?
Breakaway on the fuel line.
We have to have the fuel lines break away. And there's actually two kinds out there. There's a slight difference in the way they operate, but the basis is the same. Okay? Here are those breakaway fittings. Okay? And what happens is we have a fitting that looks just like this, and what you have is your female end and you have your male end. And this is just one type, but the basis is pretty much the same. Okay? And what happens is as those lines break away, those pins are going to shear, and when they shear, there's a heavy-duty spring in there. That heavy-duty spring is going to take that access door and it's going to slam it closed. So the only fuel that you're going to lose is that little bit of fuel that's right there, which is insufficient for post-crash fires. Okay? And until recently, between the Koreans and between us, it was supposed that we were not supposed to be able to have a post-crash fire with basically the way the system worked. And in most crash scenarios, that's held true. There's two accidents that they're looking at. One was that Korean bird. You'll notice as it hit the bridge, it burst into flames. That's what they're talking about. The way the system's rigged, that's not supposed to happen. Okay? So they're looking at that one, and then one in Afghanistan or Iraq, the one that had the R&R. There was a post-crash fire on that one that they're looking at and what the cause was. But part of it is that because that fuel's not allowed to leak, there shouldn't be any fuel residue, fuel fumes that can be ignited and catch fire. And this is part of that system. Now, I've been playing with this one for a long time, and I have yet to get this thing to budge. So you can see, and that's just one type of fitting. And we'll actually show you the fittings. This is the one type of breakaway fitting. And the way this one works is just like this. Again, you have your door. As it breaks away, it slams that door closed, trapping that fuel and preventing that fuel from escaping and being able to get out. This is the other type of fitting, the one that's being passed around. And again, like I said, very similar in nature. The door closes. When it breaks away, sealing it, preventing fuel from getting out. Those are the two types, and you'll notice the overall means is pretty much the same. It seals those lines, preventing fuel from being able to spill. Next, we have to worry about our electrical connections. Now, everybody says, well, if the lines or if the wires just break away, no harm, no foul. Wrong. Because what happens is there's a possibility of arcing and sparking. So what they did is they took advantage of the quick disconnect fittings that are already on there to facilitate maintenance. We pull back on that sleeve, which pulls a locking pin out and allows that cannon plug to disconnect. All they did was hooked a wire right here to allow the tanks, as they break away, to do the same thing. It pulls back on that sleeve, allowing those pins to come out, allowing that electrical connection to quick disconnect. But here's the problem, gentlemen. People don't realize the point of this cable. And therefore, they don't really take it seriously. I've found those on pre-flight and daily. I've found them either broken, I've found them not attached, and when I've gone up to people, they said, yeah, we knew. What do you mean you knew? That's part of the crashworthiness of the system. If those wires are broken or not connected, then we're going to be tearing or breaking those wires, which means we're going to have exposed wires, which means we're going to have arcing and sparking. Kind of defeats the purpose. So you have to know that you need to look at those. Any questions about that? Rollover vent system. Now, the first thing we'll discuss before we go on break is, why do I need a vent system to begin with? That's the first question we need to ask and answer. Why do we need a vent system to begin with our fuel system?
Well, there's probably a couple of reasons. The altitudes at which we operate.
Okay, what else?
Bladder.
It's a bladder system, meaning what?
Expand, contract.
Okay, but as I'm sucking out fuel out of that bladder, what's going to happen to my bladder? It's going to start to collapse unless I let what occur? Unless I allow something to get in there. And what are we going to let in there? We're going to let air take the place of the fuel as we suck it out. Therefore, that bladder won't collapse. Make sense? But now, we have some other scenarios that we need to talk about. What is it? One, where does it actually vent from? Where does it actually vent from? It actually vents from the bottom of the aircraft. Good job. Now, why is that important to understand? How will fuel venting manifest itself to you? How will fuel venting manifest itself to you? To us.
Well, you probably smell fuel vapor.
Smell. That is the primary way that it is going to be identified. Now, here's the other misconception. Okay? Fuel venting is a very bad thing for this aircraft. Why? Because as those bladders expand, and they will expand, they can actually expand to the point where on the main tanks, there's 3 major formers that run behind there. They will bend those major formers, which means we need to be able to identify it and handle it really quick. But the problem is that people waste valuable time because they don't understand the process of fuel venting. What is majorly going to cause, or primarily going to cause, fuel venting?
Pressurized.
Overpressurization caused by what, Bus? Bus says I answered that part. You all help me. Okay, caused by what?
Refueling.
By refueling. Okay, I'll buy that one, but what else? What else do we have to specify?
Excessive fuel consumption. There has to be a leak.
No.
Temperatures.
That's all going to factor in, but that's not what I'm looking for.
The movement of the aircraft, left, right.
Okay, now what I'm looking for. What would cause me to get into an overventing situation? What type of operation did we say the transference of fuel from the aux tanks to the main tanks was? It's a refuel. So if that operation doesn't stop like it's supposed to, what's going to be a result of that process? Overpressurizing, overfilling it, which is going to cause that venting from the bottom. If it starts to get too excessive, then it could vent from the top. But if it gets to the venting of the top, we've probably done major structure damage, which is why you have to realize what should be your first primary concern. See, this is why it's important to kind of understand.
Just from what you said, if I smelled it, first thing I would do is check the operation if I am in fact pumping from the aux fuel tanks.
Okay, so how would you check that?
Well, you can
It sounds good.
You get the pump switches on, and do I in fact have fuel by checking the indicator pumping, based off my burn rate?
Okay, where am I going to check? And see, this is why I want you to have a good concept. Where are we going to check?
Checking your fuel quantity gauge if it's more than 2,000 pounds in the main tank.
Thank you. Notice he didn't say aux tanks. He said he went straight to the main tanks. Now, reality is, you might even want to consider just turning off the aux pumps until we figure out where it is. That way we'll minimize the possibility of doing damage to the system. Just something to think about, which is why understanding the system is so important. Let's go. So we were talking about the rollover vent system prior to going on to the break. Any questions so far? So we understand why we need the air to be able to get in there. We understand in the case of the fuel venting where it's actually going to vent from. And keep in mind, can it vent from the top? And we'll show you the top vents here in just a second. Yes, but only if we let it get that bad. Hopefully we catch it before it gets that bad, which means it should only be venting from the bottom. Any questions about that? Now, as we look at the rollover vent, everybody complicates the crap out of this thing. Reality is, what we had to do, I say we like I had anything to do with it, what they had to do to keep this a crash-worthy system is they had to let air get in, but prevent fuel from getting out. Agreed? So what you're going to find out, and actually this picture does a better job. Where the picture that we used to have to simplify it so you could see it, in simplifying it confused people. But what happens is, because the vent's way down here, and based on which tank you have, this is an aux tank one, which means the main tank one is even bigger. Agreed? But all the tanks have them. And then based on the lines running up to here, it's going to allow air to come in and then get vented into the tank at the top and take the place of the fuel as we're sucking it out. Good? Now, in a rollover scenario, what's going to happen is as it rolls over, what was meant to be a vent is now going to be on the bottom of the tank. Agreed? And here's where everybody gets it complicated. Can fuel get into here? Yes! We can't stop it from getting into here. Okay, so how does it prevent fuel from being able to get to the vent? Well, now, if this becomes the bottom of the tank, then the bottom of the tank now becomes the what of the tank? Top. And was the fuel all the way up to this very, very tippy top at the beginning? No. So in the rollover scenario, is the fuel going to make it all the way up to the very, very top now? No. And then what's going to happen is as the fuel as the aircraft continues to roll over, should that occur, the fuel is going to go through the path of least resistance, which was what? Back out the same way it came in. Agreed? So it's nothing more than because of the height of the fuel and the amount of lines in there, the fuel is only going to come up and fill the lines in relationship to what the fuel level was in the tank. Does that make sense? Everybody understand that? Don't look afraid, Bus. Okay, I know you're getting it. So what it looks like is this. First off, this is showing you an empty tank. What do we have to do? We have to put fuel in. What's in the bladder right now?
Air.
Air. So we have to let the air out. So as fuel comes in, quite simply, what's going to happen is it's going to force that air to the top, causing that air to be vented out so that fuel can go all the way up. Agreed? As we suck the fuel out, the opposite's going to occur. Keeping in mind that it's painting a false impression up here. Okay? What they wanted you to see was that the air was coming into here and taking the place of the fuel as we were emptying it. But they decided to go outside of the tanks. Keep in mind that the people that helped us make these are not 47 people. They read the material, that was the concept they pictured. But what was happening, and we're actually going to just rewind this so that everybody sees. What's happening is as that fuel's coming out, yes, we're venting the fuel out either via this valve or down at the bottom, because what's happening is that air is actually going in through those lines and going out through these two vents. One on the top of the aircraft, one on the bottom. Good? As we suck the fuel out, what's going to happen now is that air is being sucked back through, and that air is only coming into the top of the tank. It's not being vented outside anywhere, which is the picture that this kind of gives you. Any questions about that? Now, as we look at the vent, you'll notice that it's coming around. We have this sump area right here. All this sump area right here ensures is fuel is heavier than air. Everybody agree with that statement? So if any fuel gets up to here, it will fill this bowl, and only the air will be able to get in. Does that make sense? So all it is a little sump catcher that prevents and ensures that only air goes through those air lines. Is there going to be a little bit of residual fuel in there if this aircraft were to roll over? Sure. And reality is this is just in case. And that fuel's heavier than air, and it will fill the bowl, allowing only air to be vented overboard. Any questions?
And then what, as the air passes over, what residual fuel's in there, it just evaporates?
Exactly. Exactly. Anything else? So that when it rolls over, again, the vent's now in the bottom of the tank, but that fuel is still only going to come up to whatever that fuel level was prior to the rollover situation. But it wasn't all the way up to the very tippy top to begin with, so what makes anybody think that it's going to make it to the tippy top now? And that's what keeps it from going over the vent or going out of the vent. Now, as it starts to roll back over, that fuel is going to go through the path of least resistance, which is going to be right back out the way that it came in, so it's still not going to end up at the top. Any questions about that? Now, here's your vents down at the bottom. And what you have a vent and you have two drains. Okay, this serves as a drain and a vent. Why? Because this is at the very back of the tank. This is the lowest point. So guess what this is also going to be used as? Not only a vent, but it's also going to be used to take the fuel sample. And what happens is you just put a screwdriver in here, which is going to push up on a valve, you turn it, and it allows fuel to actually come in here and go out what was normally meant to be a vent. Good? So you can see where the circles are your vent portion, and where the fuel drains, you put a screwdriver in here, and actually we have a special modified, we make a little funnel type system that puts it up there, and we just take the fuel sample using that. Any questions about that? The other drain would be for if we were going to empty the tanks, if we were going to drain all the fuel out, but then you'd have to have 5-gallon cans underneath the tank. Normally when we defuel it, it defuels sufficiently that we don't really mess with these very often. Any questions about these? Okay, now, the thing about the tanks that we have to remember is this aircraft is capable of doing water landings. Because it's capable of doing water landings, where did we say the vent was? On the bottom. Well, if I do a water landing, now where's the vent?
Bottom.
On the bottom. It's underwater. So what happens is we have a system in here that prevents water from being able to come up that vent. And so what you have is as water comes into here, just through the vent, it's going to float this ball up, which is going to push up on this mechanism that's going to block it. Should this one fail, there's another one that will act as a backup to prevent it from allowing water to get in. But now, here we go. We've landed on the water. We're still sucking fuel out of those tanks, aren't we? So have we eliminated the need for air to get into those tanks? No, we haven't, have we? So what we have is we have a secondary vent system on the top of the aircraft. And it looks just like that. Okay? Under this fiberglass cover is your actual vent. Just like a snorkel, it's going to take over if the primary vent, which is the bottom, is sealed or blocked. So it will still allow air to get in. Again, it will also be part of the fuel venting process only in the case of what? It gets so bad that not only is it venting out the bottom, it'll vent out the top. And by the time it starts venting out of the top, we probably have done major structural damage. Which is why it's important that you understand and recognize it as fast as possible. And you can see on page 14 of your handout, the high vent pipes also vent fuel in the event of fuel venting from the bottom. The pod exceeds 9 gallons per minute. It actually attaches a number to it. But that's the only time that that becomes a factor. Any questions about that? Now, there's one more thing that we need to talk about. In doing the water landing, we have a requirement of what?
50%.
50%. Where? You're shortcutting me. 50% where? In the main tanks. Now, why do we have that requirement? And here's what we've got. Let me grab the black first. At the very bottom of the tank is a hole, a vent. And what you have, what type of system did we say we have?
Rollover
For-
fence system.
What?
Rollover fence system.
Okay, now what I'm looking for. What?
Bladder.
A bladder. So inside of this shell, we have a bladder. Now, why does that become important to understand? What was this bladder made out of? Rubber. Well, what happens as temperature changes and they've got a cold fuel inside of there? What's going to happen on the outside of this bladder system? It's going to form condensation, right? Now, if we trap that condensation into here and didn't let it out, eventually what would happen is this area would fill up and then we'd end up collapsing the bladder on itself. Agreed? So what we have down here at the bottom of the tank is a hole that we don't close up. And it looks just like that. Just like a hole. Cool, huh? But what the hole has is it has a little clip in there. Now I know you all noticed this on pre-flight because you all saw it. Okay? This is known as a critter clip. It's made to keep rodents and birds and stuff from going in there and making nests and stuff like that. But this hole can't be sealed up, which means if we land on water, water is now going to go in there and still do our same thing that we were concerned about if we didn't let the condensation out. Because of the area inside the main tank, it will allow sufficient water to get in there that would result in collapsing that bladder, which would not be good. The other thing about it is there's sufficient area that enough water might get in there to float that bladder too, which is your other concern. Okay, so now, what's the problem? The ox tanks have the same thing too. So why isn't it a concern on there? There's not enough area to allow sufficient water in there to actually collapse that bladder. And for a long time, it's easy to use terms like area and sound intelligent, but reality is a lot of people still don't get the concept. And I was listening to Wayne teach not too long ago, and really, he gave us the perfect example, okay? If you take a ping pong ball material, okay, and if I blow it up real big, and then I have my little ping pong ball still, if I were to push on that big one, what would happen at where I'm pushing it? It would collapse, right? Why? Because it's so big, that force is enough to push it in. Agreed? But if I took a little ping pong ball and I applied the same force, what happens to the ping pong ball now? Nothing. And note the key word, same force. Could I push it and collapse that ping pong ball too? Sure I could. But we're not talking about that. We're talking about equal pressure, equal force. With that big bladder, it's going to be more reactive. Where because those aux tanks are a smaller bladder, it would take an increase area that's non-existent. So therefore, that's why it's not a concern. Any questions about that? Make sense? All right. Fuel boost pumps. 115/200 volts AC. We had electrical yesterday. Now it makes sense, right? DC controlled, AC operated. Normally, the left side is going to be powered up via the number 1 electrical system. The right side is going to be powered up via the number 2 electrical system. But keep in mind, we're not talking about with a bus tie or without a bus tie. We're just talking normally. That's how it's powered up. Everybody understand that? Which is why yesterday when we talked about an electrical failure without a bus tie, one of those results is the fact that those fuel boost pumps, those electrically operated fuel boost pumps, are going to quit operating too. Now, as we look at the fuel boost pumps, and I'm going to pull them both up here. Okay, right now we're looking at a fuel boost pump in the main tank. Here's the one for the aux tank. The pumps themselves are identical. Okay, the pumps themselves are identical. The pumps don't change. Fair enough? Good. Now, we'll talk about that in more detail here in just a second when we actually get into the pumps. But located by the aft pump in the main tank is what's known as your pickup, or there's your pickup for your engine-driven fuel pump. And you can just barely make it out back there. There's your pickup for your engine-driven fuel pump. Your aux pumps, again, the pumps themselves are the same. The only thing that changes is how this one's mounted, which is the one in your main tank, versus how this one's mounted. This one's mounted into this special housing, which mounted to this housing are your 2 thermistors. Now there's another fancy-dancy term, thermistors. What in the world is a thermistor? A thermistor is nothing more than a heat-activated switch. I'll say that again. A thermistor is nothing more than a heat-activated switch. That's all it is. Now, how does it work? As long as fuel is keeping those thermistors cool, those pumps are going to continue running. But if those thermistors are uncovered, then what's going to happen is they're going to heat up and they're going to cause that pump to shut down. Which is why, gentlemen, as we're flying along fat, dumb, and happy, as those aux tanks empty themselves, do we ever reach up there and turn off the aux pumps? Nope, no requirement to. Other than seeing the low pressure lights come on, verifying that those tanks are empty, that's it. That's all we do. Why? Because the pumps themselves have already been turned off via that thermistor system.
Why did they become warm? Because of the pump?
Because there's no longer fuel in that tank, and now they're allowed to heat up. As long as both those switches are covered and their fuel's keeping them cool, then they won't heat up.
How many degrees do they react?
You know what? I don't know.
Because if I'm flying in Alaska, they're not going to warm up. So it's going to be like a difference of 4 degrees instead.
That's a good question. I'll look it up and see if I can get that answer for you, Buzz. But you know what? I've never had anybody bring up that point. But they will heat up, and I know Alaska, they work just fine, Tom. So we can sit here and we can worry about it, but reality is Alaska's flying CH-47s. They're not modified. They work the same way and they do just fine. But I will find out what it is, Buzz.
Thank you.
No problem. Good question. Any questions about that? And we'll show you more. There's that bell mouth fitting, and you can see that there's a line that comes in. And this is back there in the main tank, right next to the aft pump. Why is that important to understand, gentlemen? Where that bell mouth fitting is. What is the bell mouth fitting actually for? That is where your engine-driven fuel pump is actually sucking fuel out of its associated main tank. Now, why is that important to understand? What caution do I have in my operator's manual?
Nose low attitude.
Avoid nose-low attitudes. Now, reality is, if you pay attention to your PPC data, this should not be a factor. Okay? Why? Because in the case of a low fuel pressure, to get the max extended range, we know what airspeed we're going to go to, and that's going to give me a fuselage level look. Okay? But when we tend to get low, what sometimes is our mindset? It's just like what we do in our car, right? Uh-oh, I'm almost out of gas. What do we do in our car? We speed up, and in that way, as soon as I run out of gas, hopefully I got sufficient speed to coast a good distance. But if I go into I got to hurry up and get there, and I put this aircraft into a nose-low attitude, and it's using those engine-driven fuel pumps to suck the fuel out, now what's going to happen is we're going to suck air into that system. And we will end up flaming the engines out based on where that bell mouth fitting is. Any questions about that? How many of those do we have?
Six.
Should be 4.
Two. One in each main tank. And they're located in the same spot on both sides.
So all that is physically inside the tank.
That's inside the tank, yes sir. That's inside that bladder to be exact. And this is your aft pump in your main tank. That's where it's close to. Now, our jet pump. We talked about a line that allows fuel during refueling process to transfer from the right side of the fuselage, right side of the aircraft, over to the left side. We said there was a line that runs directly underneath between those two forward intertank areas. Agreed? Does everybody remember that on that first picture?
D1 non-attached.
Yes. D1 receptacle is attached to it. It allows us to refuel all 6 tanks simultaneously. What I failed to mention is that is your only non-crash-worthy line. That is your only non-crash-worthy line. Which means what? Which the next best thing is to render it safe.
Clean it out.
Empty it out. Empty it out. Therefore, we didn't care if it was crash-worthy, because the only time that there's fuel in it is during the refueling process, which is when we're on the ground. Agreed? So what's going to happen is in the forward intertank area associated with the forward main pump of each side, we have what's called a jet pump for the process of evacuating fuel out of that line. Now, if anybody's ever had a waterbed, you're familiar with this process. If anybody's ever had a waterbed and you've had to empty it out, you're familiar with this process. It works on the same principle. So what is that principle? This is your line between that refueling pressure line pressure refueling line that runs underneath the forward inner tank area. There's a line on the back of it that's going to go up and associated with the forward main pump on each side. So there's actually 2 of these jet pumps. This is inside the tank itself. Everyone tracking where we're at? And you'll notice it's at the front of the tank. Again, we're talking the forward inner tank area. Now what I'm going to ask you to do is go to your page on 16, page 16, which you have a picture just like this. So everybody's on the same sheet of music. This red, different color of red right here is signifying the fuel that is in that pressure refueling line. Everybody understand that? Now, in the top left, this is going to be pressurized fuel via that forward pump in each one of the main tanks. Good? Now, we're going to go ahead and run it through. And what you're going to see is as this pressure fuel comes through this line, what's going to happen is a Venturi effect is going to be created right here. Why a Venturi effect? We're going to have low fuel pressure down here. So what happens when a high fuel pressure meets a low fuel pressure area? It creates a suction or a Venturi. That suction and Venturi is going to suck this door with the aid of this fuel weight. It's going to suck it open, now sucking and evacuating the fuel out of that line and putting it right back into the forward main, into the main tank itself. And it's going to look just like this. Now, once this fuel is empty, what's going to happen is this weight is going to go away, and now this spring, which are these dots, are going to supersede the pressure, and it's going to close that door back up. So therefore, once that line's evacuated, this process is no longer in effect. So now that line has no fuel in it. But now, what's our next concern? In talking about what we just described, as that fuel's evacuated out of that line, what would be the tendency based on what we just described so far?
Well, what happens after that shuts and you still get that pressurized fuel being pushed?
Not what we're looking for, not exactly. It's going to work on the same principle as that bladder, isn't it? We're sucking fuel out, so what would it want to do to that line? It would want to collapse it. Agreed? Because it's just working on the same principle. And what would happen if we took a line and we collapsed it, expanded, collapsed it, expanded, collapsed it, expanded, collapsed it, expanded, collapsed it, expanded? Eventually it's going to do what? It's going to weaken over time and it's going to break. That's not a good thing, right? So what happens is through the D1 receptacle, air is going to be allowed to take the place as we evacuate that fuel out of that line. And in allowing that air, it's going to do the same thing as the bladder. But what's going to happen is that air is going to come in from one of two places. One of these will be a vent, allowing air to get in. Second, this door is not very sealed very tight. So air can still get in through here. It's not made to stop it. So therefore, air is going to be able to take the place as we evacuate that fuel. Any questions about that?
What stops after it's complete and it's, let's just say what ends up really happening is that line becomes repressurized from the outside. Air.
Well, it's not. All we've done is we've sucked air in.
There's pressure in there. I mean,
Yeah,
you can't-
insignificant pressure.
Yeah, but what happens to the pressurized fuel supply from that main fuel pump? What shuts that off?
What had happened was when this fuel was evacuated, there was no weight on this side of that door, so therefore this spring was able to overcome it and close it. And in closing it now, although that pressure fuel is still going through there, it hasn't stopped. Because there's no weight, that air pressure is non-existent. There's no weight to it. That spring is keeping that door closed, so it's not doing anything. It's just circulating.
I see what you're saying, that fuel's still going into the main tank.
Yes.
That jet, okay.
Yep.
It's both from the main tank, right? The left's in the main tank,
Yes, sir.
it's going back into the main tank.
Yes, sir. And there's one on the left and there's one on the right. So basically what we're doing is, as long as we turn on both forward main pumps, we're evacuating that fuel in both directions. If I just turned on one pump, it would still evacuate that line.
It's only for internal use, only for this use.
It's only for that use, exactly. It does no other purpose.
2 forward pumps are only to evacuate the fuel line.
No. It's also going to pressure fuel to the tank. But this process, this jet pump, is only connected to the forward pump. Which means what? Here we go. Let's make sure we're all on the same sheet of music. We fly from point A to point B, and we take on gas. As long as we're going to take off again, do the crew members have to worry about evacuating that line? No. Why? Because as soon as we get ready to crank this aircraft, as soon as we turn those main pumps on to fly, that process is going to happen naturally. Good? But now, if we bring it back to garrison and we're done for the day, our requirement as enlisted crew members was to evacuate that line. Why? Because by that fuel sitting in there, it's going to cause that rubber to dry rot, and eventually it's still going to crack. So we leave that line evacuated at all times. We never leave the fuel in there. Now here at Mother Rucker, you may not see that process because the POL handlers actually do that process for us. The crew members don't stick around and wait for the fuel truck to come, so they automatically do that for us.
So what do they do, crank the APU and run those fuel pumps, or the?
Yes, sir. Yep, we'll crank the APU up, APU generator on.
They only need to run one pump.
They only need to run one, but it's faster if you use it on both sides. Any other questions? Good questions. Good job. Now, pressure refueling shutoff valve. I'm going to show it to you, gentlemen. But right now, all I'm going to tell you is that each tank has one. So how many of these fuel shutoff valves do we have? Each tank has one. 6. And I'm going to tell you that it is for the refueling process. It is for the refueling process. This is what's going to be used to stop the transference of fuel from the from the truck to the aircraft. But in the main tank, what did we say the transference of fuel from the aux tanks to the main tanks was?
Refueling.
It's a refueling process. So guess when this is also being used in the main tank? During that transference of fuel from the aux tanks to the main tanks. And we'll talk more about that here in just a second.
Well, it works both ways.
What do you mean both ways?
Because it's a shut-off valve, so it shuts off,
Yes, sir.
primary and secondary.
Yes, sir.
So it goes to the auxiliaries, then it shuts off.
Well, we're going to show you exactly how that works. That's why I'm not passing it around right now. At this point, all we need to understand is that we have one in each tank, and that it's for the refueling process, keeping in mind that the transference of fuel from the aux tanks to the main tanks is a refueling process. It's just a mid-air refueling process. So therefore, this is going to be a factor when we talk about that process. Any questions about that? Okay. These are our high-level controls, and we have one of these in each one of the tanks. So how many of these do we have? We have 6. Why 6? There's one in each tank, which makes sense because we're going to tell you that this is going to be used for what process too?
That pressure in that valve when we use to shut off the,
It's going to be used to shut off this valve. What was this valve used for? Refueling process. So guess what? This is going to be used for the refueling process, but keep in mind, the one in the main tank is also during what process? The transference of fuel from the aux tanks to the main tanks, which was nothing more than what? A refueling process. So it's going to use all the same pieces and parts. And again, you notice I'm not passing these around yet. So we will go into the nitty-gritty of how it works in a moment. Right now, all we want you to understand is that we have one in each tank, and that it is for both the refueling operation and, in the case of the main tanks, the transfer of fuel from the aux tanks to the main tanks, which is nothing more, quite simply, than a refueling process. Main tank fuel probes. You can see the actual locations from outside of each one of the tanks, and you'll notice we have 3 probes. We have 1 for each one of the aux tanks. Now, the fuel probes themselves, here they are. Here they are. Here's what they look like. Okay? Basically, this is what you see on the top of the tank. And what you're going to notice is you have an inner tube and an outer tube. You got an inner tube and an outer tube. And we'll show you the picture here. Now, this is a center probe. Just keep that in mind. That up there is a center probe. This right here is any other probe other than a center probe. How do I know that? It doesn't have a low-level thermistor on there. Which is, what is a thermistor? It's a heat-activated switch. It's a heat-activated switch. That's all it is. And here's how it works. What you have is you have that inner tube and you have an outer tube, and then you have these little standoffs that prevent those 2 tubes from contacting each other. All right, now, this is a capacitance type system. Why is it important that you understand that it's a capacitance type system?
because it doesn't use a float.
Okay, but what else? Why is it important that you understand that it is a capacitance type system?
That requires electricity.
Okay, it does require electricity. What else? It automatically factors in the type of fuel that you're using. So there is no reason for you to have to sit there and say, okay, I'm using JP4, it weighs 6.4 pounds per gallon, as opposed to JP8 that weighs 6.8 pounds per gallon. You don't have to do that. Because this is a capacitance type system, that's automatically factored in. Fair enough? Good. Now, what's going to happen is a small, minute amount of voltage is going to travel down that inner tube. So what's going to happen is fuel is going to be able to come in between these 2 tubes, and fuel is a conductive medium. Meaning what? Meaning now it's going to allow power or electricity to transfer from that inner tube to that outer tube. Just kind of using a variable resistance signal. The higher the resistance, the higher the amount of fuel. The lower the resistance, the lower the amount of fuel that's in those tanks. Any questions about that? And we're going to pass these around. You can actually see the rubber standoffs. Be careful, because the tube will come out either direction. And I'd hate to see you be the one on camera to let it fall and hit the floor. Now, we said the main tanks has how many of those probes? 3. Now, again, the signal goes from the aft probe to the center probe to the forward probe. From the forward probe, it goes up to the selector and to the indicator. And it's going to send the average of all 3 probes.
But the center one, that's the low level.
Yes, sir.
Why don't they take all the low level of those probes as well?
Because based on that forward probe or that aft probe, it may be higher or lower in that fuel level than that center probe will be. The center probe is a good average of where the fuel level is, and that's why. Okay, and again, all it is a thermistor, so it's just nothing more than a heat activated switch. Any questions about that? Okay, there's your low-level thermistor. Your low-level thermistor, again, is only connected to your center probe on your main tank. We know we're going to empty the fuel out of the aux tanks, right? So do I need a low-level indicator for that? No. Do I know when I've ran those aux tanks out of gas? Yes. How?
Low level thermistor on your pump.
Your advisory light.
Your advisory light on the overhead panel, but then I still have to do what? I have to confirm that there's no fuel in those tanks. What tanks? The aux tanks. Now, this low-level thermistor, based on where it's mounted on the probe, and that's all it is. Why 320 to 420? Because based on where it is, it's a little bit variable, so therefore it had to have a range. And approximately 20% of fuel. Any questions about that? Okay. Learning step activity 3, and what we're going to do is we're going to go ahead and start our 10-minute break, and then we'll carry on from here. Any questions about anything we covered so far? Then we're going to talk about learning step activity 3. Describe the operational characteristics and airframe mounted components of the fuel system, for the fuel system. We're going to start off with the overhead panel. By now everybody knows it's located on the overhead, about middle of the center row is where you're going to find it. And reality is, this tells you everything you really need to know about the fuel system. It has the schematic, and of course, what type of questions are they going to ask you? How many pumps are connected to your fuel system? All you have to do is count the switches. And that's going to help you with that process. As we look at it, again, you've got a pump. You've got a switch for every pump. You got a 2-position switch, off and on, keeping in mind that it's going to go from the aft position or upper position to forward or down position when you turn it on. Allows you to control the pumps individually, but reality is, when would I have to turn off pumps? Normally it says all fuel switches on, cross-feed closed, right? When would I have to do anything different than that?
Fuel venting.
Fuel venting, yes sir. What else? So for an emergency procedure. When else?
Crossfeed.
No, not what I'm looking for. When would I have to turn those pumps off? And what pumps would I have to turn off?
Internal loads?
What?
Internal loads?
Not internal loads, no.
Oh, when you're doing what he just, you have to turn off your aux tanks when you're refueling with the IRFs.
Ah, when we're flying missions with IRFs on board, we turn off the aux pumps, we pump off the internal tanks first, and then we'll switch to the outer tanks. Why? That way if those pumps fail, or we have a problem with any of the IRFs tanks inside, then we know we still have our external tanks. Now we'll test them, we'll check them, we'll make sure they're working, but as soon as we do that, we'll turn off those aux pumps, allowing us to use the internal tanks first. Keeping in mind that the internal tanks are still pumping into which tanks? into the mains. And that main tank fuel is going up to the engines or the heater or the APU, depending on what we're talking about. But reality is, by this time we're flying, so our main concern is our engines. So that would be the only time that I'd have to turn them off.
So you never tend to make switches off?
You just turn off the aux fuel pumps. You have to leave the mains on, but reality is the same things are applicable. As long as I'm below 6,000 feet, those engine-driven fuel pumps, regardless of where the fuel's coming from, it's going to suck fuel out of those main tanks.
So the only reason for the main fuel switches is to check if the crossfeeders work? Pretty much? Because you never turn
The
them off.
only time, yeah, the only time that we use the main ones is for troubleshooting and checking. That's affirmative, yes sir. We will always turn those on, we will always leave them on. Reality is we don't need them, so why do we turn them on? It just puts less wear and tear on these engine-driven fuel pumps, making them more reliable for when we do need them. So we're pressure fueling up to the engine-driven fuel pump, and from there we've already talked about the process.
So all the pumps are working at one time if all the switches are on?
Yes, sir. It's a constant process. When all those pumps are on, what we're doing is we're transferring fuel from the aux tanks to the main tanks. The main tanks are feeding the engine, and this process is continuing on the whole time. Any questions about that?
The ERFs, you got their own pumps.
Yes, sir. The ERFs
They're
have their own
located
pump.
on the ERF itself,
They're actually located on a pump board that's mounted to the front tank.
so they can control it. It's something the flight engineers.
Yes, sir, that is a fact.
But yours
So what
work.
they'll do is they'll check it. Once they confirm and they feel good that the aux tanks are pumping into the main tanks just fine, then they'll turn off the aux pumps and they'll tell us to go ahead and turn on the ERF's tanks from the rear. And we have gauges back there to monitor them, and we have a pressure indication on the system just like what's happening up front. Why? Because it's an identical system. Now, ERFs 2 is an identical system. Now ERFs 1, we had these makeshift fuel indicating systems that sometimes they worked, sometimes they didn't, but reality is we had to monitor those tanks. Where with this one we have a gauge that tells us when they're empty, and it's the same process of what happens up front. Our aux fuel pressure lights. When any one of the aux tanks has less than 10 psi plus or minus 1, plus or minus 1 is always a parameter for everything. Okay? So 10 psi plus or minus 1, if it drops below that pressure. Now keep in mind that these pressure lights, we have one pressure light, but it's monitoring both tanks. Both the left aux tanks and both the right aux tanks. The left one is monitoring the forward and aft on the left side. The right one's monitoring forward and aft on the right side. So they're both connected to the one switch. So if one fails, we will still get that light coming on. And then we'd have to confirm whether or not it was a pump or if the tank was empty. Any questions about that? Keeping in mind, it's a weird phenomenon, but reality is, even if one tank started off with slightly more than one tank full of fuel, say there's 10 gallons different between between the forward aux and the aft aux. It's kind of funny how somehow they'll equal each other back out and then they'll burn even. Same thing when we fill this thing up. Okay, and you'll notice it when you fill this tank, the aircraft up. Even though the left tank might have had less fuel than the right tank when we started, they'll equal each other and then they'll all kind of fill up at the same time. The main tanks will have fuel, the auxes will be completely empty. The auxes will catch up with the main and then they'll all come up pretty much simultaneously. It's weird, but that's the way it happens. Okay, fuel is going to go through the path of least resistance. Which one has least resistance at that point? The empty tanks. So they fill each other up, and then once they catch up and all the resistance is the same, then they all just keep filling up simultaneously. It's a weird phenomenon, but it's pretty cool to see. Any questions about that? Refueling station on and off, all that does is transfer power from the inner set of instruments to the outer set of instruments. Fuel totalizer, fuel quantity indicator. Keeping in mind that the only thing electrical in the refueling process is the fuel quantity indicator, fuel selector, and if we manually shut off or close one of these valves before the tank's full. If the tanks fill up, then the process is all fuel. It's all pressure related. Meaning what? Meaning if we had no power applied to this aircraft, we could still refuel the aircraft. What we couldn't do is we couldn't monitor it and we couldn't stop it in case of an emergency. But the refueling process is all pressure. And we'll show you that here in just a second. And then of course the crossfeed. Keeping in mind, all the crossfeed allows us to do is to pressure fuel to both engines simultaneously from one system. That's all it does. If both sides are working and that crossfeed's open, guess what? The left is still sending fuel to the number one engine, the right's still fueling to the right engine. In order to dictate which way that fuel process goes, it's based on whatever tank has low pressure. That's what's going to happen. Okay, whether you turned off the pumps or whether the pumps weren't working, what's going to dictate which way it goes is it's going to go high pressure to low pressure. That's the way it's going to go. Now, this fuel pump relay box is behind the soundproofing. We're just showing it to you because reality is this is where the signals go to. And then it goes up to the cockpit. Everybody's kind of sometimes under the impression that it goes straight to the cockpit, so they don't understand how it dictates or determines the average fuel before it goes up to the gauge. It all goes to a relay box which does all that. Okay? And also provides for all the electricity. At the top you got your aux pump thermistor control. Why? Because in order to turn on the aux pumps, it has to check those thermistors first, which makes sense, right? If those thermistors are not covered, then it's not going to turn that pump on. Do we sometimes decide, man, we got to pick up a real heavy load, we're only going to top off the main tanks? But sometimes we get in the habit of doing what? All fuel tanks on, crossfeed open, or crossfeed closed. Boom, 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 boom. Oh, those tanks were empty. Guess what? You're still not going to hurt anything. Why? Because the system's protected by these thermistors. We'll actually talk more about them here in just a second. But there's the thermistor control unit on the top of that relay box. When we talk about the main system, now this is nice to see. Reality is, are any of you going to remember this? Nope. It's just so that you can see the checks and balances with the relay box and how it actually activates. When you turn on the pump, when you turn on the switch up in the cockpit, here's what's going to happen. Now, why? You'll notice that it's 28 volts DC. In this case, we've got the number 2 system on the right side. You'll notice that it pulled 28 volts DC, but it's also pulling 115 volts AC. Why?
DC control that stuff, right?
Exactly. All that this is helping us do is reinforce the fact of what? If we lose the DC switch or we lose the DC power, we're still going to lose the pump. That's all that this is reconfirming. Fair enough? So they go to the switch, to the relay box, and now it's going to go to those pumps and activate it. What's actually going to the pumps? AC power. Any questions about that? Now, the aux tanks are a little bit more complicated in the fact that what? Not only do you require both AC and DC, but we also have to factor in these thermistors. Because what happens is with these thermistors, both the thermistors have to be covered to cool them down sufficiently to allow that pump to be activated, and they both have to be uncovered to heat them up to the point that it's going to shut it down. Why 2 switches? What's that going to help with? What process?
Yeah, one for turning it on and one for turning it off.
Okay, kind of, sort of, but why do we have the 2? Why don't we just have the 1? We only have 1 for the low level. Why do we have 2? What process are we trying to eliminate? What's going to happen with that fuel in that tank? It'll slosh, right? And we don't want these pumps cycling on and off. Why? What's left in those tanks? Vapors. What do I know about vapors? They have a very low flash point. If this pump's allowed to cycle on and off, what people don't realize is the fuel that is being moved through this pump is also keeping it cooled and lubricated. So if there's not sufficient fuel to cool and lubricate this pump, it's going to heat up, and now we got the possibility of igniting those vapors in there. That's why it requires both those switches to be uncovered and both of them to be covered to turn back on and off. So now, here's what the process looks like. Okay? Again, we're going to go from the switch. It's going to pull 115 volts AC, and it's pulling up in the top right-hand corner 28 volts DC. Why? Again, DC controlled, AC operated. Just reinforcing the fact of what? If I lose a DC system, I'm still going to lose the pump. If I lose the AC system, of course I'm going to lose the pump. But a lot of people forget that association, and that's why we're showing you this. This just helps reinforce it. But now what's going to happen is it's going to go to that control unit that's located at the top of that relay box. And then it's going to go to the thermistors and check it. Right now, what's going to happen is because there's no fuel inside that tank, it's not going to allow power to go back and turn the pump on. If we were to put fuel in that tank and now cool it down, the thermistor is now going to go ahead and send through the various relays, and now it's going to allow the pump to turn on. Any questions about that? And that's all that this is showing. Now, your fuel pressure switches. Anybody want to take a wild guess how many we have? How many? 6. Say it with confidence. 6. Why 6? We have 1 switch associated with each tank. Now, the ones for the aux tanks are in the inner tank areas, both forward and aft. So we have 2 on each side of the aircraft in the inner tank areas. 1 is inspectable and 1 is not. Which one's inspectable? Sounds like a trick question, but it shouldn't.
Forward.
The forward. Why? Because those are the only ones that open. That aft area, it's sealed unless you want to take off a whole bunch of bolts to pull that plate to be able to look in there. But that's where the other pressure switch is. The ones in the inner tank areas are for your aux tanks only. The ones in the inner tank areas, both on the left and right side, are for your aux tanks. The one on the front or the forward inner tank areas for the forward aux. The one in the aft inner tank areas for the aft aux. Good? They're going to be activated when pressure drops down below 10 psi, plus or minus 1. So this is one of the aux ones. Now, remember we said that there was some confusion sometimes in the fact that when we open the crossfeed, people sometimes are under the misconception that we're transferring fuel from one side of the aircraft to the other side. We're not. The next concept that they get confused is they think we're transferring pressure from one side of the aircraft to the other side. And what leads to that confusion? They're not dumb. There's something in the system that leads to that misunderstanding, which is what? When I open that crossfeed, what am I looking for? I'm looking for both fuel pressure lights to go out, ain't I? Well, if I'm not transferring pressure from one side to the other side, what's causing that to happen is where the location of that pressure switch is, which is on a manifold that's located on the back of the aircraft, and in the ramp area, you can see it. If you were to stand on the ramp hinge, there's my cockpit, there's the back of the aircraft. If you stand on that ramp hinge, if you take about a step and a half back and look to your left and to your right, you're going to be looking at a manifold that allows for either fuel to go the normal route up to the engine or the crossover route up to the engine. That manifold is where that pressure switch is. And because of where the pressure switch is, that's what causes the light to go out. We're only talking about the fact that we're sending pressurized fuel up to the engine. That's all we're talking about. It still gets activated at 10 psi plus or minus 1. This is the right side of the aircraft. How do I know that this is the right side of the aircraft? What?
Yeah, everything was only this right side.
What is it?
Yeah.
I-
The utility, the
Okay, I got my fill port, which I know is on the right side of the aircraft. Good job, Larry. What else? How about my defueling system? Is my defueling system associated with both sides of the aircraft?
No.
Nope, only my right side. So this is my right side of the aircraft. This manifold right here, if you could see right here, fuel would be going up to the engine on that side of the manifold. The crossover line, it comes through here, and we're going to show you. We're going to show you that line, that system here in just a second. Okay? Fuel pressure lights. There's the one for the left, forward and aft aux. This is the light for the forward and aft aux on the right side. Keeping in mind that although we only have one light, there's still two pressure switches. One pressure switch for the forward aux tank, one pressure switch for the aft aux tank. It just has one single indicating system. And then, of course, the ones back on the ramp area are the ones that turn on the lights on the master caution panel / advisory panel. Now, here's the crossover line, and this is the crossover gate valve. And here's a close-up of it. Now, here's that pressure switch we were just talking about. Fuel normally is going to come up this line through this gate valve, which is electrically operated via what? What's that gate valve electrically operated via? Fire pull handle. And then it goes up to the engine. But if we use the crossover line, that fuel's going to come down here, come through this manifold, and go up to the engine. As long as this manifold is pressurized, then that light is going to be out. And again, we're looking at what side of the aircraft? The right side. And there's one on the left side too. And we'll show it to you here in just a second. Now, these gate valves, here's the gate valves. And they all look the same. They all look the same. What look the same? The two for your engine fuel shutoff valves. One on the left, one on the right, one for the number 1 engine, one for the number 2 engine, and each one of the crossover gate valves. Now, what's the problem with that? A lot of people question, why do I need 2 of them? Why don't I just have one for the crossover line? Where would I put one valve that's going to allow me to trap fuel in that crossover line? If I put it in the center, then the fuel's going to drain back out and that crossover line's going to be empty. If I put it on the left side, then it's going to be empty because it's all going to get sucked over to the right side. If I put it on the right side, then it's going to get sucked over to the left side, leaving my crossover line empty. So when I open that crossfeed valve, the first thing I'm going to be sending up to that engine is air. Not good, right? But by having two of them, when we close them, now we're trapping fuel in that line so that when I open the crossfeed, I'm going to be sending fuel almost immediately up to that engine. And I'm limiting the amount of air possibility. Any questions about that?
So if I open my cross feeds, and for example my right main tank is empty or pump's not working,
Yes, sir.
I'm going to close the valve. I open the cross feed, but I close the other one.
Nope, you're not doing anything. Because there's a lack of pressure on the one side, that's going to dictate which direction through that crossover line that fuel's going to go. Okay? So in other words, here we go. Ah. Okay, and all I'm going to do is draw the main tanks, because that's all we really care about. Okay? We got a pump here, we got a pump here, pump here, pump here. Any one of which can provide sufficient amount of pressure to pressurize the fuel up to the engine. Okay? Back here we have our crossover line. Valve here, valve there. Good? Now, when I open the crossfeed, both these valves are going to be open simultaneously. Good? If these pumps aren't working, that pressurized fuel is going to go through here, and it's going to feed this engine still, and now that pressurized fuel is going to feed this engine.
But to stop the fuel up there, I have to pull the fire handle.
No,
Can it go backwards to the other tank?
no. There's a one-way check valve we're going to talk about here in just a second. Back here in the system, there's a check valve that prevents fuel from being able to go back into the tank. Good point. Okay, Bus. Good job. Nope, there's no need to. There's a one-way check valve. Good point. Good point. We're going to get to it, actually. We're going to show you the check valve. That's why I'm trying to be very careful. The check valve comes out, actually. Okay? Now, what we have are a series of lights associated with the valves. That light is going to come on. Listen to the way I word this. Those lights are going to momentarily illuminate when this valve is in transition. Meaning what? Meaning those lights have nothing to do with whether or not this valve is open or closed. Those lights don't care. All those lights tell me is that this valve is in the current act of transitioning. If it's not in the current act of transitioning, then those lights are going to be out. Whether it's open or closed is irrelevant. Now, if these lights are not working, what is going to be my requirement? Can I still fly the aircraft, or is the aircraft grounded?
It's still probably flight. No, you have to manually move.
You're partially right. You went too far. Okay? He's right. We can still fly the aircraft. Why can I still fly the aircraft if those lights are not working? What do we have the ability to do? And I'll give you a clue. Pre-flight.
Check the light.
We can check them. So even though the lights are not working, I can still physically go over there and look at the valve, and I make sure that they're in the right positions. So therefore, we can fly all day long.
What is the intent for the flight engineer from the forward part of the cabin area to see those move in an emergency procedure?
Yeah, it's just a means of being able to quickly identify, yes, it transitioned. If in my mind I already knew it was closed, and I see that light come on, then I know it went to the open position. If I knew it was open and I see that light come on, then I know it transitioned to the closed. And we check them, right? we do our pump check, and then we do our crossfeed closed, and then what are you going to hear from the rear? Crossfeed closed, lights are out. These are the lights they're referring to. But the actual lights they're referring to is the fact that we have one for the right valve on the crossfeed, and we have one for the left valve. Did these lights do anything? No. Why not? I didn't pull the fire pole handle. So when we say lights are out, we're only talking about the lights associated with the crossfeed. Any questions about that? Okay. And there's a close-up of the lights. And they're going to correspond to their individual valves. Keeping in mind that, again, they're only telling me that that valve has transition. They haven't told me whether it's closed or open. How do I know whether it's closed or open? I can physically read closed, and in this case I have it open. And what you're talking about is a valve that slides out of the way like a guillotine. If I were to slide it, you'd see a piece of sheet metal come across that closes it up, and it's sealed, and that stops the fuel from being able to go through there. Good? But now, you'll notice I was playing with a handle. Those valves are also, in the case of an electrical failure, we can manually operate those valves too from the rear of the aircraft. Any questions about that? There's the engine fuel shutoff valves, which we said are electrically operated via the fire pole handles. I think we beat this one to a dead pulp. Everybody should understand the pre-flight value now. Everybody should understand what valves you're looking for to be in what position and why. Are there any questions about that? All right. And there's your fire pole handles. Any questions about that? Now what you will notice, and I will highlight it this time, is it works off the 28 volts DC from the essential bus. Why am I going to highlight that? One, we've had electrical class now. And two, when is the essential DC bus activated? When the battery switch is on. Meaning what? Meaning until you turn the battery switch on up in the cockpit, if I had manually closed those valves on you, remember for your training process we were talking about? Until you turn the battery switch on, and if I did that to you for training, I would also, as a courtesy, I would come over the intercom and say, "Sir, ma'am, the engine fuel shutoff valve has opened." As a courtesy, if I manually closed them on you for training purposes. Otherwise, you won't hear anything. Any questions about that? Now, I promised you I would show you that check valve. Okay, this is that manifold that we were talking about. Whether the fuel's coming up the normal means, going up to the engine, through the engine fuel shutoff valve, or whether it's coming through the crossover line, going up to the engine. But here's that one-way check valve. And when we show you that one-way check valve, it does have a bypass capability in case of a thermal. In other words, what? If that line heats up, what will happen is you have a bypass capability to allow that pressure to bleed off. Otherwise, you'd risk overpressurizing the system. But for the most part, and you'll notice all of these check valves tell you which direction they're operating. And what it does is it will prevent fuel from being able to go backwards in through the tank. Because again, we're talking low pressure versus high pressure. It's going to want to go through the path of least resistance, which based on the fact that gravity is going to take it down, plus pressure, it would want to go back in through the, over to the other main tank.
How much does it bleed? Because if your tank is leaking.
Very, very low. Oh, it won't. It won't. It's insufficient. The only time that is if it's statically and it pressure from fumes and vapor are higher than just the normal pressure. And that's why. So normally it will not bypass. Thermistor, Have we already pretty well covered this? Keeping in mind that the thermistor is nothing more than a heat-activated switch, and we said it's going to turn on our low-level light up in the cockpit anytime the fuel is between how many pounds?
420 and 4.
320 to 420, or how much in percentage of fuel? 20% of fuel. And it's that thermistor's connected to what? The center on the main tank. The center on the main tank. Everybody understand that? Okay. Fuel quantity indicator. Those probes. When you look at the indicator, it's going to tell you fuel capacity in pounds. And we already covered the fact that it already factors in based on the type a system is, a capacitance type system, whether you're using JP4, 5, 8, low lead, or avgas, Jet A, whichever one you're using, it'll automatically factor in the weight based on the way the system works. The gauge itself has both a digital and an analog system. The needle is the analog system. Your digital system's in the inside. But this is a fuel totalizing system. Why is that important to understand? Why is it important to understand that it is a fuel totalizing system? How does your fuel system work in your car? Is it a totalizing system? No. As you're using the fuel in your car, what's going to happen to that fuel indicating quality? It's going to keep coming down, right? Now, what's the problem in this aircraft? What if my fuel in my aux tanks become classified as unusable? What will my totalizer tell me?
That fuel is still available.
That fuel's still available. So what would I have to do? If my aft aux tank has 500 pounds of fuel remaining in it, and I classify that fuel as unusable, even though my totalizer says 550 or 5,500, I have to remember it's minus 500, so I only have 5,000 pounds of fuel. And I have to make my adjustments to my emission as required. That's why you have to remember that it is a fuel totalizing system. Any questions about that? I'll go one step farther. I'm not usually a negative person. But if I was going to tell you anything negative about the CH-47, the fuel totalizing, the fuel quantity indicating system, in my opinion, just stinks. When you need it the most, it becomes the most unreliable. When you get into that low level, when those lights are illuminated, you never know what that indicating system is going to do. So if I had to say or point out a negative, this would be it. So my word to the wise, if you have an opportunity to take on fuel, take on fuel. But you've been told that your whole Army aviation career. Fuel selector allows us to select the individual tanks, and that is what is actually can control the analog system. So the needle is going to point in pounds what each one of the tanks have based on the fuel selector position. Now, the other thing that you have probably already been told, the fuel quantity indicating system is incredibly slow. So you either want to check all your aux tanks or check all your main tanks. You don't want to check an aux, then a main, then an aux, because you're going to end up having to wait for it to come back down. You got a question?
Nope, they're all AC powered, so you can't see what's on the aircraft until you apply AC power.
Yes, sir. Yes, sir.
Not even the one outside.
Not even the one outside. Which means we're going to end up talking about a what? Because I know that I can refuel this aircraft with just the battery plugged in. But as you just pointed out, both the totalizer and the fuel quantity indicator are AC operated, 115/200 volts AC. And actually, when you turn on the overhead fuel refueling station, all you're doing is taking that power from the inside indicating system and transferring it to the outer indicating system, as well as you're now powering up that panel to allow us to refuel the aircraft. And all it allows us to do is monitor the fuel quantity, and it allows us to electrically operate the fuel shutoff valves to limit the amount of fuel that we put in a tank. i.e., if I'm going to carry a 1908 and I only have 5 minutes of flight time, I know that I cannot get to a 1908 with a full bag of gas and hope to pick it up. The gun itself and crew with an 822 bag is 19,200 pounds. If I don't burn off sufficient amount of fuel, by the time I get to that weapon system, I'm not going to be able to pick it up. So you might end up telling the crew member, hey, top off my mains, I only want 400 pounds in each one of my aux tanks. And we can manually do that. That's what we need electricity for, and we'll show you that here in just a second. Okay? So as it's already been pointed out, it is an AC system, so it does require AC power to see what the fuel quantity is. This is the fuel quantity switch box. Why are we showing it to you? Just so that you understand that that's the process that it's going through to dictate and determine what indicating system that we're actually attaching to. Describe the operational characteristics and components of pressure refueling. Here we go, gentlemen. When we look at the tanks, again, we can single point refuel all 6 tanks simultaneously. We can single point refuel all 6 tanks simultaneously. And we already talked about the phenomenon where if the aux tanks are empty, the main tank still has fuel, the aux tanks will catch up to the main tanks and then they'll all come up fairly evenly. Okay? Now, as we look at the process, what's going to happen is in the right forward intertank area is going to be your D1 receptacle, and we'll actually show it to you here in just a second. Fuel is going to go to each one of the individual tanks on the right side, and we'll talk about how that happens here in just a second. Through that pressure refueling line, fuel is going to go over to the left side and then refuel the left side simultaneously. Again, this is the only line that is non-crash worthy, but it's only part of the refueling process. How do we render it safe? Via the jet pumps. And how are we rendering it safe? How are we rendering it safe? By evacuating the fuel. If there's no fuel in there, we don't have a problem. Okay? And again, we told you that the aircraft can be refueled in approximately how long? 4 minutes or so. All right. Let's see. And we'll talk about the process as we go along. Okay. Single point refueling. The 4 minutes is based on the following: 300 gallons per minute and 55 psi. Again, Army trucks are not capable of pushing that. Army trucks are not capable of pushing that. They normally average between 35 and 40 psi, and they normally pump about 215, 240 gallons per minute at the outermost. Okay? But the Air Force can blow us away, the Marines can blow us away, the Navy can blow us away, and any civilian airport. So we have to monitor it, and we have to be aware of it. Also, the power requirements, you'll notice that it says 28, 24 volts DC from the switch battery bus relay, keeping in mind that the switch battery bus relay is available simply by doing what? What?
Turning on the battery?
Turning on the battery. There it goes again. No. When is the switch battery bus available, gentlemen?
Battery's connected.
As long as the battery's connected. So we can refuel just by having that battery plugged in. But the indicating system is still 115/200 volts AC. It's actually 115 volts. So there's an inverter, and we'll talk about that. And the battery switch does not need to be on for this process to occur. Refueling station By turning it on, all we're doing now is diverting the power to the panel, both for the fuel selector and the quantity, and the ability to electrically operate the valves via these high pressure floats. This is how we can manually shut them off. What we are doing is electrically shutting them off, which is going to manually shut this valve. And we'll actually show you that process here in just a second. Now, again, if I do not do anything with this switch, can I still refuel the aircraft? Sure I can. Sure I can. Why? Because the refueling process itself is all pressure. Has nothing to do with electricity.
It's gonna do them all simultaneously.
It'll still do them all simultaneously. The shutoff system will still work. Everything will work just as advertised. The only thing that won't happen is I won't be able to monitor fuel quantity, and I will not be electrically able to shut valves to limit how much fuel I put in a tank. Now, one other thing I have to cover, depending on which modified aircrafts you have, if I have refueling station on, what will happen is it will deviate or divert the power from the indicating system inside the aircraft out to the refueling station. When does that become a big deal that we have to be aware of that? Hot refueling. If I go to hot refuel this aircraft, you're not going to have any indications up in the cockpit. And that's why, as a courtesy, they let you know how much fuel you have on board. There are aircrafts that are modified where both of them can still remain powered up. But how many are out there, I don't know. Who has them, I don't know. And again, the power on allows us to power up that refuel station. Any questions about that? We pretty much have already covered that. The inverter. Inverter is located behind the soundproofing on the right side of the aircraft. Approximately 220, 240, give or take a little bit in that area. You have an inverter that's going to do what? What does an inverter do? DC to AC. Any questions about that? As we look at the refueling station, we'll get into all the switchology now. There's your fuel quantity indicator. The fuel quantity indicator inside the aircraft and inside the refueling station state are the same. As a matter of fact, if the one becomes inop, we can take it right out of there and put it up front and have on several equations. Selector is the same thing. Now, these refueling valves. In the aft inner tank areas, listen to me carefully. In the aft inner tank area is another set of valves that when you turn the power on this refueling station, those valves need to transition from closed to open to allow the aft tanks to refuel during the single point refueling process. I'll say that again. When I turn the power on, a set of valves inside the aft inner tank area have to go from the closed position to the open position to allow the aft tank to be refueled via the single point pressure refueling.
If it goes via the main,
It goes through the main, yes sir.
from main to aft and forward.
But that's not the main focus on it. You'll actually see why. Okay? I'll show you why that valve is important here in just a second. So bear with me. It is a line that goes through the tank. Okay? But these lights right here indicate that that valve has, guess what? Transitioned. It doesn't tell me it's open and it doesn't tell me it's closed. So how do I know if it's open or closed? When I go to refuel it, if the valve went to the open position, I take the selector to the aft and it will tell me that I'm taking on fuel in the aft aux tanks, we're good to go. Okay? Now, when I power it down, I'm looking for the opposite. Those lights are going to come back on momentarily, telling me it's transitioned, and I'm presuming that it has closed. But when will I be able to confirm it? During your fuel consumption check, during your cruise check, you're verifying that the fuel from the aft aux tank is transferring to the main. if that valve did not close, what will happen is that fuel transference will not occur. And now we're what? That fuel is classified as unusable. That fuel is now classified as unusable, so now you're going to have to take it out of the fuel quantity system. Any questions about that? These allow us to manually restrict how much fuel we put in an individual tank. For again, the purpose of allowing us to pick up greater loads with less flight time, or if we know that we're already going to have to pick up a heavier load, we can restrict fuel on the aircraft, but that will restrict how much time we can fly. Dual control floats. Now, what we have is we have two different types of systems. We have one for the aux tank and we have one for the main tanks. Okay? Allowing for two different processes to occur. And we will actually show you that here in just a second. Now, how many of these did we have? 6. Why 6?
Each tank one?
Each tank has one, okay? Now, as we look at these high-level floats, what happens is we have a line connected to them for the primary and secondary off. Here we go. There's your primary, and they're marked. You can read. Okay? You got one that's marked primary and one that's marked secondary. And then you have the aux tank floats, and they do work different ways. So here's how they work. You got 2 floats here. Why? Because it's a dual float system. We got a redundancy. If primary fails, secondary will kick in. If secondary fails, then primary will kick in. So we have a redundancy to make sure. Keeping in mind, when does this get used? When's this process going to occur? During refueling operations. But keep in mind, in the main tank, it's also going to be part of what process? It's going to be part of the transference of fuel from the aux tanks to the main tanks, which is nothing more than a what type of operation? Refueling operation. Okay? Now, here's where the electric solenoid are connected, and here's your 2 solenoids. And what you're going to find out is down at the bottom, those electric solenoids are going to control this valve or this flap, which is actually going to push up on this float, which is going to cause these high-level shutoff valves to close your fuel shutoff valves. And believe it or not, we're actually going to get into the process here in just a second. And they're electrically controlled. So now, here's what the process looks like. What's going to happen is, as fuel comes in, it's going to float these 2 balls up. As it floats it up, it's going to come up. Fuel's going to go in there, floating it up. And what happens is, it's going to restrict fuel, because what's going to happen is now, in this valve closing, what's going to happen is it's going to create a back pressure that's going to result in closing this valve. Now, here's the 2 floats. You got a big ball, big red ball, and then a white ball in here that seals it closed, and then that fuel's allowed to overflow it and fill the bowl. Floating this float up, which is going to close a valve inside of here, causing a back pressure that's actually going to go result in going back here and closing this valve. And this is the one that's in your main tanks. So as fuel comes down, ball's going to be open, allowing that fuel to come back in. Any questions about that?
This also stops the pumps from the main or the aft and forward to pump into the main.
Yes, sir. Yes, sir. It is for both processes, which is why this one has to work the way it does. Okay, where the aux ones work a little bit different. Okay, this is the fuel shutoff valve, and you can see you got the primary and secondary. This is where that back pressure is going to come back into. And what you actually have is two doors in here. And so this is what's going to happen, okay? Fuel's going to come in here. As it comes in here, it's going to go up both the primary and secondary and go into the bowl, but it's actually going to come out a back port. What you have back here is a port that's going to allow that fuel to squirt out the back. Because why? Because I'm not ready for the fuel shutoff process to occur yet. So what's going to happen is it's just going to drain out, allowing that fuel to access out here. Okay? As the fuel gets in there and in the aux tank, it's going to fill up that bowl via that fuel floating that valve up, which is why the aux tank is a little bit different. Okay? You'll notice you don't have the float. And what this one's doing is waiting for the fuel to overflow into the top, where this one's actually filling the bowl. Until the fuel comes all the way up, it's just going to drain right back down into the tank. Now what's going to happen is once that bowl is filled up, what's going to happen is it's going to create that back pressure, which is going to result in pushing that door closed. And you'll notice it did the secondary and then the primary, which is why there's a slight delay or slight difference. Now, as I promised you, gentlemen, as I promised, here's that gate valve we were just talking about. When you power up, that light's going to momentarily come on, telling you that that valve has transitioned. We don't know whether it's opened or closed yet until when? We take on fuel. If I take on fuel and that fuel is going into the aft aux tank, then we're good to go. If we take on fuel and fuel's not going into that aft aux tank, that means that this valve has not transitioned to the open position. Now, why do we have one associated with the aft, but we don't have one associated with the forward, which is the next confusing thing? And what I'm going to do is I'm going to use the cursor for the computer. What you're looking at is the left side tanks. Everyone tracking? Fuel's going to come through here, and it's going to come through here, and it's going to go into this forward aux tank. Good? Fuel's also going to go through this one-way check valve, and then it's going to fill up this main tank. Tracking? Good. Then it's going to continue up here, and it's going to go through here. It's going to drop down here, and if this valve is closed, this is where it's going to stop. We tracking? If this valve's open, then it will go through here and it will fill up the aft aux tank. Now, when I power the refueling station down, this valve has to close again. Here's why. As we suck fuel out of that aft aux tank, it's going to come up here, and what's going to happen is it's going to want to go through the path of least resistance, which is going to be which way? It's going to be back down here, and if this valve is not closed, it's going to go right back into the aft aux tank. So basically, it's just going to be cycling in there. As long as this valve is closed, then it's going to cause it to go down here, hit this one-way check valve, and then it's going to fill the main tank. Everybody see that? So if this valve doesn't close, I'd rather have it remain closed than remain open, because at least the fuel for the flying portion is usable. If the valve doesn't open for refueling, can I still fill that tank? Yes, but it just means I have to gravity refuel it. But I can still use it if I need it. Any questions about that? And there's that fuel gate valve. Keeping in mind, this is actually in the aft inner tank area, which is why we can't look at it. Defueling nozzle, we already said that that's used to defuel the aircraft. Reality is we use it to steal fuel from the aircraft.
Go one picture back. We can't see that, you say?
No, sir, you can't see that one. This is in the aft intertank area, which is all bolted up and screwed up, and you can't see in that area.
Why?
Why?
We're missing, if it doesn't work, we're missing a lot of fuel. And it would be very easy to just make a small hatch and just open it manually, or close it.
During refueling operations, the only time we use it. If it doesn't work, if we really need the fuel, what can I do? I can go ahead and pull all those bolts and I can manually get into there. If I need it, okay? If I don't need it, then it's no harm, no foul anyway. So if I need to, I can pull all those bolts and I can still access it. And then I have to disconnect the electrical connection, otherwise it'll electrically go where it's told to go.
I was gonna say, what's the purpose of those lights on the panel for the transition part if it's not there to at least give you a heads up of potentially, hey,
That's all it is. It's just a potential, hey, you might have a problem, so you need to pay attention. Other than that, that's all it's for. Okay, any other question? Okay, in order to defuel using this system, we have to power up the aircraft. It's not made to just suck fuel out of that. In looking at the IRFs 2, we have 3 800-gallon pods that we can carry. We can use it for either a FARP, forward area refueling point, meaning what? Meaning we can use this gas to transfer it to vehicles or other aircrafts behind us as required. Here's the first tank and your control panel for actually monitoring and controlling the pumps to the system. All operated via the crew member, and you have your fuel quantity indicator that will only tell you how much fuel you have in the IRFs. And it has a selector for which IRFs you're looking at. And you can manually control either pump, controlling and dictating what the order is of pumping fuel. And we pump it which way? 3, 1, 2. For the purpose of what? Why does it matter how I burn it out of there?
Balance.
CG. Okay? The tanks themselves are a Kevlar tank. They are a bladder system, just like your external tanks. They work just like your external tanks. And keep in mind that we can refuel all 6 tanks and 3 internals all simultaneously if we want to. Not advisable. Why? Because we want to monitor the flow. We want to monitor the fill port. So we normally do either the external and then the internals, or the internals and then the externals. But if we need to, we could do them all simultaneously. The vent system, why? Because it's a bladder system. It needs to get air in there just like we talked about before. Any questions about that? Now the vents are actually on the side of the aircraft for IRFs 2. For IRFs 2, for IRFs 1, where was the vents?
Oh, the cabin area?
On the top of the cabin area there. So there they are. There's the old IRFs 1. This is the valve that has to open to allow us to refuel the internal tanks using the D1 receptacle from the forward right intertank area. And this is actually in the left intertank area. And that's actually electrically operated from inside on that pump board. So here's the pump board. There's your refueling switch. That's what controls that valve. Individual pumps to dictate which tank we suck the fuel out of first. That's all that's for. Fuel quantity based on which tank. We can only monitor one tank, and it has lights. And we're not going to make a big deal about it because that's a whole nother. Here's the fare kit, which is for your forward area refueling equipment. This will contain all your hoses, pumps, receptacles, nozzles, everything that you need to run a FARP or a fare system. Cool, huh? That happened in Afghanistan or Iraq. Describe the fuel system emergency procedures, cautions, and warnings. Now, this is directly out of your Dash 10. Now, in talking about the floats, if the if the aux tanks dual float system doesn't work, can we still fly the aircraft? Yes, we can. Why? Because we can manually monitor the tanks, and it's only going to be applicable during refueling operation. Now, if the main tanks, primary and secondary, don't work, can I still fly the aircraft? No, I can't. Why? Because the transference of fuel from the aux tanks to the main tanks is a refueling process. If they didn't work for refueling while we're on the ground, then it's not going to work for that process, and we're putting ourselves into the possibility where we're going to get into a fuel venting situation right off the get-go.
If you're not using the auxes at all?
Well, if you're not using the auxes, then that would be a special parameter. But if you're using the aux tanks, which we normally do, then you can't fly that aircraft. You have to fix it before we fly.
So you can fly it with, I'm
If-
trying to figure out what the book says, wouldn't,
The book says you can't fly
at all.
at all without repairing it. That would be a special consideration for wartime or possible scatter situation. Aux fuel pump failure, keeping in mind, how do we determine a failure of the pump versus an empty aux tank? If I get this light in conjunction with fuel remaining in the tank, then it's the pump that failed. Now what do I need to remember? That fuel is now classified as unusable. Any questions about that? If I get this light and there's no fuel remaining in the tanks, then the tanks are empty, and that's okay. It did its job. Fuel venting. Again, what would happen if I didn't select a main tank to identify which side is the problem? What if I just reached up there and turned off all my auxes? Have I created a problem? Not really, because I can still troubleshoot it and figure out which one is venting. But what I possibly have done is saved the aircraft from the possibility of structural damage. Because if we get into that fuel venting caused by what? The transference of fuel from the aux tanks to the main tanks,